Welcome back to Cloud Computing and Big Data. Now we arrived at the final lecture of the course, and that allows us also to reflect a little bit what we had in the whole course. But we want to do this in a different way, as you know, typically going into direct content and so on, but rather thinking on what are the long-term ideas you can get out of the course, how basically the course material is reflected in job descriptions, which is of course an important topic for many of you. So we will see that much of the content we had here is always a little bit incorporated on job descriptions. But before we go into the material of the epilogue, let us briefly review what we had the last time with OpenStack, because we will come back to OpenStack today when we look on some job descriptions. So we have learned that this was in the lecture essentially also flipping the view again at the end of the course, similar like today, that we have to think about the situation when, you know, basically your boss comes into your door and in a company and says, well, create our own cloud in-house, right? This could be different reasons we discussed, like sensitive data, medical data, for instance, or even the car manufacturers we discuss with the new car designs, you know, new car features, which are usually also often simulated, often analyzed with AI and so on. That this is all basically a little bit, you know, coming into the play when you rather want to have an in-house cloud. That doesn't mean also that the public cloud vendors that we know, like AWS and MS Azure and Google Cloud Platform, et cetera, that they are unsecure, right? Of course, but it could be also reasons where, you know, medical patient day of one country should be not leaving the country in regulation. So it could be also these aspects that, you know, influence the decision of creating a private cloud. And of course, that doesn't mean that there are hard boundaries. As we know, with Kubernetes, with Docker containers, you can ship them around. For some applications, it may make sense to, you know, first use a public cloud, maybe for testing on public data, before you then ship the same container with all the same algorithms, with all the same source, etc., then to your private cloud with private sensitive data to analyze. So there are different use cases where you can think about a hybrid cloud, right? Which also is basically now the idea with OpenStack. You have a private cloud, combine it maybe with some services which are in the public world, and then you have a hybrid cloud. So, but let's not talk too much about these things. You have seen that before. Also, the OpenStack, you know that this is a very huge topic. There's also CloudStack these days, another, let's say, interesting building block we would discover if we would have more time in the course, but the time is extremely limited in the course. That's why we could not, you know, review everything, but we have actually carried some of the fundamentals of OpenStacks where we said, well, it provides you nice components for compute, networking, and storage, which is a very nice view from the top, enabling you then essentially infrastructure as a service here with virtual machines, bare metal, but then also enabling you going platform as a service, software as a service with fancy containers, perhaps a very good UI. There's UI components also in OpenStack, which then actually can mimic pretty much, and you can recreate it if you want a little bit how it really looks in the public cloud vendors, which are sort of very professional because there's lots of money there. But maybe some of them, you know, are also overdoing it with features. So here you can, of course, build your stack with the features you need, while in the open, you know, open cloud, public cloud vendors, you have often 300, 400, 500 services, which may be all not needed in a company. So here you can tune your basically cloud stack to the needs. And we have also seen last time in the lecture that when you dive now in this fundamental building blocks here with the OpenStack shared services, you will have really jointly services, you know, combined to be deployed. You have also building blocks like Nova, like Sun for containers on the computing side. But then you also remember, like AWS had a little bit the object storage, block storage, file storage. You can also basically create this in-house with the Swift, Cinder, and Manila. Around that needs to be quite some orchestration of all these different services. For instance, with Heat, you want to have some monitoring, and one key component also is the identity management. Think about that many people probably will use a cloud inside your organization, and you don't want to maybe, you know, add them manually here and there. There would be also interesting mechanisms where, you know, basically you maybe connect to an identity management system, etc., of the whole company that makes it then also easier using, for instance, a keystone component here. But you see, when I start talking again, we take lots of time away from our epilogue because this is a huge topic. Let us just bring, one example here where we said, okay, containers is with Sun very nice supported. And with this, you have also the beautiful interoperability now with Docker containers to the public cloud vendors. You know that the Google Cloud Platform, Amazon Web Services, MS Azure, they all support basically Docker containers. And with this, you can ship them around on the public cloud and you take the Docker container back, basically put it on a Sun compute, and then you can basically get the idea to also compute that at home or in your own organization. Now, of course, always remember when I tell these things that, yeah, there is a physical infrastructure below, right? Also like here, you see hardware. So, of course, when you build your in-house cloud, you have lots of hardware to have, right? It's not the cloud can exist on itself. And also always consider the costs coming with this. We talked about in one of the lectures, the upfront investment of hardware. Maybe it's more smarter for some of the servers to keep them in the public cloud. That's what I'm saying, because also there's hardware to be bought. While maybe some of the really sensitive aspects where you think that's really needs to stay in-house, that might be something where you then buy hardware for, because we have seen, remember the GPU example with NVIDIA. If you have Ampere cards, suddenly Grace Hopper cards, suddenly Blackwell architecture cards, there's a certain way of going forward. If you, for instance, want to have cutting edge deep learning applications supported in your company for all your staff members, which could be in the hundreds or thousands, and they really won't be having cutting edge hardware, you have to upgrade your hardware again and again, and that is of course something you have to consider. So there's a trade-off to say, do you want to recreate really the complete public service offerings? And some of them you can maybe make cheaper with it, right? We have seen, for instance, the GPU costs, right? 24 hours, or 1 hour, $40. It depends really what type of GPU you want, but this can quickly accumulate to a lot of costs. So maybe sometimes one motivation is that one often used services, let's say on cutting edge GPUs, can be done here basically also in-house. But this is really something where you have to be a bit careful, not just starting this. It would be better to analyze this, go, with your company applications. Think about which applications could still remain in public clouds and which of these are more sensitive. And then talk to your boss that came into your door and said, we want to have everything private. Then you have to show him the cost and say, or her, whatever, show the costs, what could be really then a problem of getting the new hardware again. You need a proper room for it, cluster management, et cetera, et cetera. Probably 2 more persons that manage the hardware. And instead, what you all get basically, in a way with the public clouds. But I stop here because we also wanted to talk about the Epilogue a little bit more. So congratulations to everyone. You have managed to finish the course, at least from the content of the lectures. The industry project is still going on and maybe 1 or 2 assignments. But essentially, that was the content we wanted to bring across. And we do today with the Epilogue a different perspective. We see this rather as an informal final lecture. So of course, here you see preparation for final exam. That's a bit outdated. Sorry for this. Here's no final exam and so on. This is an older slide maybe, but it carries the essence still of what we had done here in the course on the mindset, that we go through the job offers in the market, because we always have to think what we do in the course and what we learn. We want to do this in and put this into action, right? So, and with the mindset, we have at least here now the ideas of all the components, all the different facets we looked. We will also review a little bit on the paradigms. And then the skill sets is, of course, something where you have really knowledge now of concrete cloud system services, and they also will be reflected in job offers and, basically this. But think about that now you have also skill sets that you can directly apply. So basically, you know exactly how to get an EC2 with Amazon, you know an MS Azure, how to do a HD Insight cluster with Spark. All of that, knowledge could be very practical and is required in industry today, but also, of course, in the academic environment. Hence, with your skill set, you have probably also the possibility now to look for PhD positions. Or, of course, I would also offer you master's thesis topics. We discuss a little bit, but that's something to consider. And then the tool sets, is of course something which comes then with the more lower level, where you think really you have seen many tool sets now, right? And this is important, that you not just stay with the view of AWS, you have also explored MS Azure, you have basically seen Google Cloud Platform, but also the limitations of Google Colab. So there's lots of these which are really tool sets you have essentially known, but with this comes also this disclaimer that of course they will advance significantly, right? So this is something where you have to be, real. If you're interested in these topics, you have to basically follow this. And Amazon provides new services. We have seen this in large language models, right? A big topic suddenly, and all the cloud vendors provide services there. So then, of course, with this comes maybe a couple of future topics to study related to this if you're interested. Things like quantum computing, neural networks on the chips, neuromorphic computing. They're really, let's say, lots of future topics where this will have also an impact in the service offerings of clouds at some point in time, for instance, cloud computing. So let's look at the outline. So that's why we did from the different perspective, we look on the whole course comprehensively. I give you a couple of further readings and jobs reviews also live here in LinkedIn, and then briefly discuss that there are master and PhD thesis topics available in the area of deep learning, machine learning in cloud computing and high performance computing. A small peek preview to the HPC course in 2026, and the course is actually planned as a summer Aurora course in the moment, at least. So that means there will be not lectures all the time, but you will be together with other students from the Aurora International setup. This is in the making, so to speak. It's not really finalized yet, but at least that's a plan. And then, of course, some acknowledgements and upcoming events, from our EHPC workshops. So let's look cloud computing from another perspective. Also think what I promised you in lecture 0 in the prologue. I mean, parallel processing, distributed computing, you have really now fully, understood, I hope. So this is, of course, something where when you add more and more EC2s, then you automatically have distributed computing in a sense that it's not only your computer anymore, you also combine this in remote in the distributed setup. Some of the algorithms we have explored are then doing parallel processing on this distribution. So basically distributed deep learning, you have heard, right, to speed up the process, or parallel processing with RayTune, if you remember all the trials. So yeah, lots of different examples of this, let's say, approaches in cloud computing, which really makes it feasible to use. And we try to get a comprehensive approach, so not just focusing, let's say, on MS Azure and get you in all the facets of MS Azure that you can directly get a certificate there for this particular cloud. We try to really go into different cloud vendors. I mean, that's for the start, right? So we really covered, I think, Google Cloud, basically from one perspective of the Colab, but also then, of course, of the Google Cloud Platform. We looked in several AWS services, SageMaker, infrastructure as a service, EC2, S3. We looked into MS Azure, a really interesting platform for HD Insight, Apache Spark, Apache Hadoop, the kind of open source tools. And with this, we always had also certain, let's say, theories and information technologies, also by the invited lectures from Andy and Marcel and Shadi here. Right? Remember, there were also some interesting aspects related to this. Also the scalability by design, which is an important approach here in the cloud course, really, right? Horizontal scaling, more users and more hardware is required, and the whole stack should work still, and provide high performance. So here and there, important was also to give you relationships to high performance computing, right? It's a topic overlapping. Some of the high performance computing systems are very well in the cloud. Others are actually not really in the cloud yet, like our Jupyter system that was just here now in St. Louis, getting the exascale, rank, and is the first European exascale computer in Jülich that we have. So this is something what you don't find in the cloud, right? So an exascale system so easily today. However, more and more topics of access, like Jupyter notebooks to these systems, and so are getting a little bit what we call cloudified. So we would see more and more integration in the next years for usability and for practical concerns to also integrate more HPC systems in, let's say, cloud infrastructures in a way. But still think about the costs, and all of that is also an important part. And the course, addressed here and there really latest advances. So we looked in Spark, new developments, also in GPUs. I have tried to get you across, for instance, with the different generations really of NVIDIA. And remember, I'm not paid by NVIDIA. It's just they have a huge market share. So also in development pace, which is quite interesting. I did, my initial machine learning, let's say, lectures perhaps on Kepler architectures. Now we talk about, Ampere and Grace Hopper, and then also Blackwell. We have also shown you updates on the commercial cloud ecosystem. So you see, basically, if you take the slides from last year and compare them a little bit, you will see certain changes, not only because we provided short lectures, but also the look and feel of some of the services have changed and new versions came across. But still, of course, the key ideas and the paradigms we will explore very soon here on one slide will remain. So it's also for you what you learned, that not everything will dramatically change. It will be just that maybe the new GPU generations of Blackwell will be soon incorporated, for instance, in AWS services with an interesting price tag. I can tell you that probably. But this is something which we also have to see, that the latest advances is, yes, are in the course now, but you also have to observe this further if you want to stay in the field. Especially deep learning is a good example we have explored. Cutting edge trust LLM, the EU projects we have seen with large language models, all the different types of large language models, Mistral and maybe Tilde that actually are really following European values, right? So this is also an interesting concern that will be coming up and is coming up as one of the latest advances of this. So people don't want to have the large language model of DeepSeek and so on, because then it maybe don't follow, the European values so close to heart. And we had this example of book chapters, right? I don't say here, how that is now being, taken, but if you use a large language models to get a book chapter, you will see if copyright concerns, for instance, are really, taken into account. And then we had some, researchers cloud systems with the European Open Science Cloud, EU-DAT services, B2Find, B2Share, and so on, which also are interesting services to be evolved over time. But we at least covered as best as we could what the Open Science Cloud has to offer today. So from the learning outcomes then we will see here essentially similar aspects we have just seen, just that for you as a student, you can now get better into a job interview because we want to prepare you for the job market, right? So this means not that you cannot do academic job interviews, of course it's the same, but this is what you now understand and really should put on your CV, as I said, with the hackathon we have done as the assignment, right? This is really something which is experience, right? And you have to put that in your CV. You understand what a hackathon is, what the challenges are, but also what the benefits of the hackathon are. These are examples of really doing, interesting deep learning, machine learning events today. And of course, using underneath high performance computing or cloud systems like Google Colab and so on and so on. And here and there, we looked really also more on these big data centers. We looked at the difference between high throughput, let's say, systems with the documents, right, where there's not a very tight interactions between the different, let's say, tasks with the MapReduce framework, for instance, right? You basically do a divide and conquer strategy. And what you really are aiming for is a high throughput of documents, analyzing them for, classifying them maybe into politics, sports, other categories, doesn't matter. But this is high throughput oriented. Hence, the whole course has this notion a little bit, while in high performance computing, what we also learned a little bit, then we have a high interaction usually between these, let's say, different cores, between the different nodes and so on. So in a way, you're basically ready to use machine learning, deep learning tools in the cloud, but I also give the disclaimer, as you remember, as in the deep learning course parts, if you really want to be, working in that field, I recommend you to take really machine and deep learning courses. This one course is based on cloud computing and big data, and deep learning is a very nice way of leveraging this. Machine learning at scale as well. But you're not really ready when you don't have a machine and deep learning course, right? There's many topics I couldn't cover here, which are important. I mean, to the most ones, you know, to combat overfitting is definitely something like regularization, learning all these concepts about that. Validation, cross-validation, model selection, also to combat overfitting with biases and so on. So these are all core topics I actually addressed very, very limited. Also, Andy and the others couldn't do that much. Hence, we have now the knowledge of using these tools, but to understand the algorithms better and the capacity of learning, a little bit of machine learning theory and more conceptual aspects are needed, like the course from you know, Stain, for instance, and so on. But also there are beautiful other courses around. I just say this is important. However, big data mining, you know, is maybe not so tough to understand. We have seen FP growth, for instance, provided by Shadi, where you don't have the large, let's say, machine learning theory necessarily behind it. You just look on data, shopping lists, and have a smart algorithm doing this. So this is something what you can basically straightforward do. You know, let's say if Kronan hires you and says, let's go through our sales, please. Can you do that in a scalable manner? Because we're actually quite big. And you say, yes, I know how to do it. And you know, you need a little bit of budget maybe for the cloud systems from your bosses and so on. But you know some of the algorithm with frequent pattern mining, FP growth, and so on. So these are the data mining strategies you also learned. And you know, basically, overall in the course, which was now the important facet, you can handle big data very well if you're using the cloud, right? It scales up and down with your requirements. And usually all the big cloud vendors have that inherently. Or if you build it with OpenStack, then of course you have to think a bit about the hardware itself, but at least the software stack can also handle basically this dynamic demands that really are there to handle this big data. Then when we look from a summary perspective now, a little bit what remains, right? I mean, a university lecture in one respect should also provide you with some paradigms we call that maybe stayed the test of time, right? So, and techniques and theory, which are basically now a bit revealed with this particular cloud vendor, with that particular cloud vendor, but they will probably stay even if cloud vendors will change or will be bought or will go bankrupt, right? So, and other builders provide. So let's look on it on a little bit on a perspective, you know, what we did in theory. So here and there we had parallel algorithms. We discussed, for instance, distributed deep learning, how to use a parallelization there, you know, to have the gradients exchange between the different nodes. Then that was really the learning, a parallel algorithm that is today used deep learning significantly to speed up deep learning. You need parallelization, and with speed up then was the idea really to make it faster, right? The training process, using more GPUs in parallel with these parallel algorithms gives you a speed up. It's also a word or theory part, which is limits maybe somewhere in the serial parts, right? So there's some laws to it, which we also more explore. Essentially, Andy did this a little bit, but of course in HPC code, we talk a little bit about then some limitations there and so on. We have seen the scalability, right? Of course, this is also a theoretical aspect of a cloud that will be remaining. So this is a core heart of it, of thinking, okay, it should be scalable, but this means lots of impacts, right? So more and more users, which then in theory use more and more storage and more compute. So how is all that reflected in your service offerings? Fault measurements, we have seen there a couple of elements which really are important. Replication, what happens if, let's say, a node goes down? We have the blocks, right, that we have in the name node, and then we know, okay, there's 3 times replicated. So if this is unavailable, I can shift the task still to another replica. So all of this fault measurement is an important facet. Technology will always fail, right? There will be always some aspects in it which, you know, are overheating, or it could be human errors even, right? That are somehow getting the cluster down, or liquid cooling. You maybe have also problems there, or whatever it is in the, you know, in the new times. There will be definitely error by design, and you have to work with it. Data mining algorithms, of course, would be another complete course, right? Statistical data mining was a course I taught once here at the university with Thomas Philip Runarsson. And this was something, you know, where, you know, there are lots of algorithms. So what we've shown here with FP growth and so on was just one of it. There are many other ones, things like clustering algorithms, k-means, dbScan, very interesting material, but would fill completely another lecture series. And however, many of those, of course, are available in the clouds, and some of them are even parallelized. Like HP DB-Scan is, for instance, a parallel version of the DB-Scan we have here developed at the University of Iceland with one of my PhDs. So there are many of these around. And I would encourage you, especially for the three topics you see here in the theory down there. We have talked about this a little bit. When you think about the statistical learning theory, we said about the hypothesis set, right? That you have a support vector machine to source from, or artificial neural networks with 2 layers, or a cutting edge transformer. These are all, basically very interesting models, but you have to put it in the relationship what data you have at hand, because you learn very quickly in the course, right? It was machine learning. Deep learning means learning from data. So in other words, when you basically have very little data set of a couple of megabytes and want to have a very high cutting edge transformer to it, this is a mismatch. You would rather maybe go to a support vector machine for classification, or for regression tasks, for logistic regression even. So this is a lot what you learn in the statistical learning theory. That's why I also say to you, combined, with the notion of saying overfitting, warning, right? So too much training. That's why we have regularization and validation. These are all topics in the machine learning course 101. And this is something you have to understand, which I could fully cover, but will also be remaining. Whatever learning algorithm or fancy new models come up with large language models, you have seen that. When we talked about large language models are nice, they work quite nice with English, yes. But when you have Icelandic or Faroese, not much text corpora around, right? So very little text. Actually, think about Iceland has 370,000 people. So very little speak the language. Then your transformer has suddenly problems, right? And there needs to be other mechanisms. Hence, this is important, and this is what you also learn then in a machine learning course much better. Also, when you think about the wide variety of deep learning algorithm, I had convolutional neural networks shown you here a little bit. Andy had a couple of examples with transformers. There's so much more in deep learning, right? There's really autoencoders for specific problems. A very interesting new field that I think will come in the next 5 to 10 years will be physics-informed deep learning. So putting constraints on the learning with physics. So basically interacting with what we would say simulation sciences from the past, doing numerical methods and based on known physical laws, and combining that knowledge and the constraints in the deep learning knowledge to basically, or learning process in a way, to really constrain it and then maybe be more accurate. And we call that physics-informed machine learning or physics-informed neural networks. There are different ways how you call it, but it's still a very interesting new topic when much things are still to come. So this is for the theory. When we look on the techniques that we had, this is also something where you would say this is something which will remain. The economics of scale. We have seen the idea of these large data centers, right, with the cooling infrastructures at scales. So this is, of course, where you can put the cost down of many of the operations instead of, would say, you have all at home a small cluster, or let's say all at home in the sense of the organization, right? So where you work. So think about it. We have so many, companies in Iceland, and they all would have their own cluster downstairs. Everybody would have hardware administrators. Everybody would have, to buy GPUs every now and then. But economics of scale, you can talk to the hardware vendors and say, well, now we create a big data centers. We actually buy not 2 or 3 GPUs. We buy maybe 3,000 or 5,000 GPUs with investor money, and then you get the prices down. One example, but the operational cost as well, right? So these are all things where you have to see that economics of scale will probably remain for many different reasons and many different views on it. From the operation perspective, if you looked on the videos with the Google data center, people roll through it to change hardware, maintain hardware. This is a very important factor, the generations, right? New generations. So this will be there. Then, of course, in memory optimizations was an interesting topic at the beginning of the course, if you remember Apache Spark. And you can transfer this to the basically world of GPUs with HBM, high bandwidth memory, as it is called. So which also basically fuels a GPU with much more memory. But you also have to know why there's a limit. Memory is very expensive, right? Of course, it's the best performance you can have, but you also go there and pay the price for it. As we discussed in the Apache Spark lecture, right? So if you want to have this, we looked at the EC2 prices with, high memory, and suddenly you pay much, much, much more for your cluster setup, right, in HD Inside, and this on a 24/7 basis, right? So hence the in-memory optimizations are of course crucial to performance, are crucial and will remain, giving perhaps the best possible performance that we have, but it will also have always this cost aspect to it in the moment, at least. Maybe there's new technology in the future that would be very interesting, but this in memory making it fast is of course an important technique. Then the idea of distinguishing between compute to data, data to compute. What I mean with this, you remember compute to data was mostly the idea now of MapReduce. You accumulate data in different repositories across the organization, and you want to have small summarization, statistics, tasks shipped to it and get it back. The high throughput idea, really. In HPC, you have always rather the opposite. You would say you have a large, Jupyter now with exascale here in Jülich, and then you would say, yeah, well, I have to ship my data there to compute it there, and then I take it away. So these are different techniques that you have to think about. So the one is much more optimized for accumulating data, maybe geographically dispersed especially. And then the data to compute is often much more basically centralized models and so on. We have learned the techniques of private public hybrid clouds is another example here. What was stretched across a course, but really at the end with the idea of OpenStack, you also got the tool set to really realizing this, right? Because we started a lot with public cloud vendors to know a little bit how the services are looking like today. But with the private cloud, maybe with OpenStack or CloudStack, there are different stacks today available. You can create also these hybrid clouds, combining the best of both worlds in a way. The distributed file systems replication schemes, again, goes a little bit with the fault measurements in a way that you want to have, let's say, data in different locations. You want to replicate it, protect it from loss, because as we said also, this is techniques which need to be there because we can always assume that the real hardware will fail at some point in time somewhere, right? So it's always good to have also techniques like replication or distributed file systems available so that you can carry on working without interrupts. And then infrastructure virtualization was a very interesting techniques to get, the system load up, if you remember, right? If everybody would have his own GPU, and we don't share it in a virtualized infrastructure or CPU or other hardware storage, then maybe, sometimes the GPU is not used because this particular person goes to vacation for, let's say, 3 weeks, and the other developers would love to have more computing power, but they're stuck to their own GPU. So this load management, right, is a very important technique factor, leveraging this infrastructure virtualization at a glance. And of course, you have to think about this directly covers and also in a sense Docker approach, right? Shipping not only any more VM images, but maybe also Docker containers around would be important. Also, there are interesting news with file system mounts, maybe by not shipping too much around, by having some dedicated libraries always at hand. But this is, of course, something where virtualization still becomes in handy. And then from the paradigm perspective, this is really now from the 10,000 feet perspective. That's something where you think this will definitely not change in the 10 to 15 years perspective, right? So these are paradigms which remain. The difference between high throughput computing and high performance computing. In high throughput computing, really thinking about the data you have, you want to analyze it with the best throughput. You don't care if there's not any interactions between the simple steps that we have seen in divide and conquer, right? So they work on their own, they generate a result, and then you do a summary out of it. And you optimize the whole system for throughput of the data. Now, in high-performance computing, we have rather number crunching algorithms that we want to really, speed up. We use many different cores at the same time in parallel and so on. Divide and conquer via MapReduce goes a little bit into the same direction as high-throughput computing, but is still an interesting aspect because I said to you also, it's this map, sort, shuffle, group, reduce, right? So it has this interesting idea of that some data needs to be in between also sorted or shuffled and grouped to do something. And of course, infrastructure as a service, platform as a service, and software as a service, there were whole lectures on it. These are different levels, really. Infrastructures more for the administrators, platform rather for developers, and softwares for the really, users. So just a couple of slides before we close for the further readings and before I show you some, jobs here online, but of course you should do that on yourself if you're really interested, and you will just give you some couple of pointers. This would be quite some interesting books to read. However, I gave you so many bibliography in all the different lectures that I would also recommend those. Of course, my teaching, a little bit self-marking story here. You will see we will further do social media on all the platforms, LinkedIn and so on, and also have the website, with new aspects. You have seen the YouTube channel will be, continued with new lectures. So if you are, let's say, go out of the university, probably there's a chance as the Cloud Computing 2026 course would be also on YouTube. So the material will be there available for you. And then let us come a little bit also on previous and current job reviews here in Iceland. You see here for an example, covering also cutting edge ideas now of this large language models we discussed. The data scientist here in Iceland was used. So if you now go essentially to LinkedIn and you type in here, where you want to have the job, but also what topic it is. I put here just AI, but AI today is a lot with large language models, right? But you see also senior machine learning engineer and so on and so on. So this is a topic we have here introduced in the course because it's really of relevance, but also there, natural language processing is also another course you might take if you're really interested in this. And you can go on cloud computing, AWS cloud security specialist. And when you look into this from the skills, you will also see and identify those things we have learned in the course. So I give you a couple of examples here, really, when you think about, deep learning, for instance, what I searched here for in this is LinkedIn jobs, right? It's something what I could recommend you, not only to enroll in LinkedIn, but also because the jobs is quite interesting there. And now when you search and find a job like here, a machine learning engineer as a remote contract, so from Iceland maybe, you will see deep understanding of data modeling, feature engineering algorithms, so things we did in deep learning, machine learning, but also here, experience with cloud platforms, AWS, Google Cloud Platform, or Azure, and deploying machine learning models in production. So of course, you cannot, maybe have everything correctly assessed, but I think some of the skills, is something where, this would be probably something what the machine learning course will then tell you, right? Using TensorFlow, PyTorch, we just did this very limited. But of course, the machine learning course will be all about this, but at least you have another checkbox here with the cloud platforms and, more of data modeling, what we had with the CRISP DM, how to work with the algorithm selection, hypothesis selection, the diagram, you remember the different hypotheses and so on and so on. The same is true maybe for more cloud topics if you search for it. So OpenStack is an example I promised you to come back to, right? You see lots of different jobs here. And also when you look now on them, if you click on one, HPC software engineer, you see HPC and clouds are very close to each other. But here you see also, Python is now everywhere. Of course, this is something also I recommend you to really look into. But you see also here the topics we have covered. You have interest and experience with two or more of the following. Kubernetes is here, what we had in the course, public cloud vendors. This is again, AWS, now Google Cloud Platform, maybe others like Alibaba or so. But this, I think, are the three main ones we covered in the course is MS Azure as well, which you really should know. But you see also OpenStack, right, is mentioned here. And you go on and go through the others and you will see again and again. I don't do that now more and more because I think you get the message. These topics which we basically had in the course are also often reflected what you have in job offers. Hence, we introduced that into the course also for changing the course every now and then. For instance, putting the containers more in and Kubernetes more and more in over the years. Then we had now large language models introduced. Of course, we have to always update a little bit, right? So the course. So let us come then to, let's say, here's another example of OpenStack, if you remember, right? So you see this is, let's say, again, in Reykjavik here with having Kubernetes, OpenStack, etc., and familiar with challenges of large-scale multi-cloud platforms, right? Scalability, more users, the metrics we discussed, growing, maybe shrinking over time. So this is all, what you learned, hopefully, and will remain in your heads. Of course, orthogonal, we had the industry project, which of course can also not cover all what is here always required, right? So with experience and so on and bonus points. But you can say that, we have some of these things with the hackathon. That was a very good example, what, you always should mention when you apply somewhere, because then you have really practical experience, done something. Even if it's not the whole cloud stack, you have done other things with machine learning and so on, but still it's valuable experience you should mention. Just a short remark that basically we have also around these topics in this cloud vendors and so on, lots of machine learning, deep learning topics with interesting data available for you for, master thesis, PhD thesis topics are also available. So maybe large language models, if you're interested, please talk to us. However, it would be always a combination mostly in my team, as you know, from, parallelization. So we will really use at scale clouds or high performance computing, right? There's some overlapping, but this is something when you have interest, then let us know. And I think it's also for you as master thesis or PhD students important that this data scientists that can really use cutting edge infrastructure like HPC clouds and good algorithms, machine learning, deep learning together, are really wanted on the job market. Then staying up to date with us and, connect to us, basically not only remote sensing here, this is one example of the lab, has constant new PhD open positions, also from Professor Gabriel Caballero now, who's also with us here at the University of Iceland, finally, luckily. So giving also lots of opportunities for a collaboration. And in the Icelandic HPC community, you have seen we have done these events now. There's a couple of them. There's one coming up at the 10th of December in the evening from 5 to 7, which I would encourage you to take. This is a little bit an error. Sorry for this. This is, of course, the next 2026 course, which is not anymore special in CFD. At a moment, it looks like we do an Aurora special course in summer. So if this not works, then we'll be back to the CFD special. But it's a little bit with university dynamics. That is what we live here, and we are every now and then, have to stick to this. But there in the summer course would be equally these topics, so much more, let's say, physical topics, where you think about, numerical methods based on known physical laws, like crash tests. CFD stands for computational fluid dynamics. We had this in one course already, very briefly touched, but should be also then going, of course, to much more details when you have the HPC course. So finally, some acknowledgements, right, through my research group, of course. So this is something, many of these members, you have seen the lecture from Marcel, you have seen the lecture from Shadi, from my previous PhD students. Shadi, Rocco, Marcel is missing here because he also finished now. Of course, Professor Cavallaro, I collaborate with him a lot in many facets. So make sure you connect to us in the Icelandic HPC community. We have still posts every time, in LinkedIn. We have now also a community page in LinkedIn, but also we have the website ehpc.is, where we will further announce the events and activities like new hackathons, for instance, the next years. Here's just an interesting timeline video for you that just maybe want to understand where HPC and cloud computing started, where it came from, with a nice timeline and having some highlights in computing really shown. So I don't play that now, but wish you all possible success in the job market, let it be academic or business. And of course, I'm also there for recommendation letters. If you want to, just contact me, then please make sure you include my assistant. Then finally, thank you very much for taking the course. It was an interesting course, a little bit here up and down with the industry project, which we introduced a little bit for the first time at the beginning of the course. We learn from that for next courses to maybe optimize this a little bit also with different lectures and so on. But of course, it's also for us a learning experience in the end, how to do these courses, especially if you have different teachers involved in that. So this is also something to really work on, and we will do. But thank you very much, and talk to you next time. Yes, maybe something I forgot. Also the YouTube community, right? I see that this is actually looked up And I got very good comments from the YouTube community at large, which goes far beyond the reach that I have here at the University of Iceland. I also would like to thank you on this very much. These is actually also used here and there in European projects to show that these slides are actually used much more broader. The logos that also give the manpower between some content that you see in the course here. So thank you all also in the YouTube community for that. And chances are we see us maybe also sometime at an event. I actually was once at event. It was the international, HPC conference we have regularly every year in summer. And there was actually someone looking my YouTube lectures already in a training that I gave on site. So it was interesting to really meet some of the remote viewers really in person. And chances are we will meet also if you are part of this interesting and beautiful HPC and cloud community. So see you then.